Hi everyone, good afternoon. Am I audible?
Yes, audible.
Okay. First of all, I request every participant to turn off your audio and video. Sir, can you please check whether you are able to share your screen or not? Okay, sir, it's visible. I welcome all the participants to the session 3 of day 4. Now we are having hands-on session on embedded system for robotic application by Mr. Ramesh Sia, Head of Vidya Center for Robotic Research and Consultancy. On behalf of the organizing committee, I welcome Mr. Ramesh Sia to handle this session. Over to you, sir.
Okay, thank you for the introduction. So good afternoon to all the participants. I hope that I am audible to you.
Yes, sir, you are audible.
Okay. So good afternoon once again. So in the last 2 days, we have discussed or we have gone through how to apply the embedded programming concept based on AVR microcontrollers for developing some robotic applications. So on the first day, we have discussed how to pass some logic high or logic 0 to the GPIO pins of the AVR microcontrollers. And on second day, that is on yesterday, we discussed how we can generate the precise timing or how we can implement precise timing in embedded programming for execution of several statements or several tasks. Like we need to, if we need to blink an LED or turn on an LED or a buzzer or turn on some motor for exactly 1 second, what we can do. So for that, we need to make use of the timer module, which is available in the AVR microcontroller. And we looked into that area, and we found that how we what is the maximum possible delay in an AVR microcontroller, because there are only 2 types of timer modules. One is the 8-bit, another one is a 16-bit. So the maximum delay can be obtained if we go for 16-bit timers. So, and after that, we calculated an approximate delay of 1 second, how we generated that approximate 1 second delay by using the scaling mechanism. Then we looked into a problem where we discussed how to generate exact 1 second delay, where the timer was initialized with a non-zero value. But then we have just looked into a basic concept of how the a robot can be moved forward, backward. That is how the directions. And we have seen that there are several directions which is possible in an robotic motion. Okay. So in today's session, we will be continuing from that particular point, and we will be looking into more detail about motor interfacing, and we will be having a demonstration of how we have interfaced the motor, and we will be doing demonstrating an example, and simultaneously you can go through a simple example to get an idea of how to run the motor. And after that, we will be looking into the control of the speed or velocity of the DC motor that is attached to the robot, and finally to the analog sensor interfacing. Okay. So today's discussions will be limited to, first of all, simple motion of robot. Then we'll be having the speed or velocity control, that is by using the concept of PWM, and then we will be looking into the analog sensor interfacing. So as we discussed yesterday, there are basic movement. There are around 8 basic movements which is possible in a two-wheeled robot, like forward, backward, left, right, soft, then backward, left, and backward, right. Okay. And from this, we have seen that if you are configuring a motor, if there are two motors, and if both of the motors are rotating in the same direction, either in the clockwise or anti-clockwise direction, then we can achieve all these possible combinations. And we have looked into the basic wiring of the DC motors, where we have seen that just by interchanging the polarity that is connected across the two terminals of the DC motor, we can change the direction of the motion of the DC motor. Okay. So moving further, it is not possible to make this change directly by interfacing the DC motor directly to the AVR microcontroller or any of the microcontrollers. And that is due to two limitations. The first limitation is that most of the DC motors that we make use of in robots will be using most of the motors requires a higher voltage than the voltage that can be supplied by the AVR microcontroller pins or any of the microcontroller pins. Mostly, most of the motors which is used in the robots, that is the DC motors, the economic series DC motors, other than the hobby DC motor. Okay, the hobby DC motor is one which we have seen, that means which has some yellow color casing. Okay, so that is known as a hobby DC motor, which can be even operated by using a 5 volt. But when we go for a little bit or an immediate level robot, a two-wheel robot, then we know that we need to make use of the economic series gear motor in most of the cases. So in that case, those gear motors needs a voltage of 12 volt. Most of the motors will be working at 12 volt, or it operates at a range of 10 to 12 volt. Similarly, the current is also more than what is required, than what can be applied by the microcontrollers. Okay, so if we look into the AVR microcontroller, we can see that the maximum output voltage that the microcontroller can provide to the output node at an output pin is 5 volt, because most of the microcontrollers will be working in a voltage range of 3.3 volt to 5 volt. Okay, so that is a maximum voltage 5, and the output current that can be sourced from a microcontroller pin will be in the range of some 20 milliampere or below. But if you take a DC motor, the current is more. Okay, so in that case, we will be using such driver ICs, which is capable of providing more current as well as switching off this potentials to different pins. Okay, so here we have a H-bridge IC. So the concept is that this IC can switch the higher potential, that is a 12 volt, to any of the required pins. Okay, so here there are two sets of H-bridge. The first one is 1A and 1Y. That is 1A is the input and 2A is input. So when if you're connecting a DC motor across 1A and 2A, by controlling, okay, by not 1A, the output of 1A is 1Y and output of 2A is 2Y. So if I connect the DC motor across 1Y and 2Y, by controlling the logic 1, that is written to 1A or 2A. So these two pins, 1A and 2A, will be connected to your microcontroller. Okay, so if I need to provide a high voltage at 1Y and a low voltage, that is a ground, okay, or 0 voltage 2Y, then I need to write a logic 1 to 1A, okay, and a logic 0 to 2A. And in the reverse case, if I need to supply a logic 1 to 2Y and a high voltage at 2Y and a low voltage at 1Y, then I need to write logic 1 to 2A pin. Okay, so the microcontroller pin which is connected to 2A can be provided with a logic high, so that the switching of this 12 volt which is applied to the L293D takes place. Okay, so since we are discussing here with a two-wheel robot, we need to connect two motors, or we need to control the motion of two motors. So I'm using a single IC here. Okay, so from here there is a small difference, that is the programs which we will be discussing in the session, just for explaining the concept, will be something related to the Atmega 328, and we will be actually implementing, or the program that is being implemented on the board which I have is different because that boat has an ATMEGA 2560 AVR microcontroller in it. Okay, so all the connections are based on that. So moving further, so on my robot, which I have the two DC motors, which is being connected across the A0 to A3. That is, since I'm having ATMEGA 2560 AVR microcontroller, it has more number of ports compared to the ATMEGA 328. In ATMEGA 328, we have port B, port C, and port D. But when we go for ATMEGA 2560, we can see that we have more number of ports starting from port A, B, C, D, F. Then we have port J, K, and L. Okay, so J, K, and L are 7-bit ports, and A to G are A to F are basically 8-bit ports. Okay, so it has been hardwired connected, it's permanently connected on the next robotics two-wheel robot which I have. So in that, the two gear motors are connected to the port A lower bits, A0 to A1, A0 to A3. So the left motor is connected across A0 and A1, and the right motor of the boat is connected across A2 and A3. Okay. Now, if you look to the L293D, whatever be the voltage that you are applying to the A1A and 2A, in order to switch the VCC correspondingly to 1Y and 2Y, or if I'm applying some voltage across control signal across 4A and 3Y, if the corresponding switching should be available at 4Y and 3Y, we need to enable. Okay, the switch consisting of 1 and 2 should be enabled by applying a logic 1 to this particular pin. Okay, that is 1-2 enabled, and to obtain output at 4Y and 3Y, I need to apply a logic 1 to 3-4 enabled pin. Okay, so here it is marked as PWM1 and PWM2. So that we will be discussing in the further sessions. So for the time being, to switch the motors across this, I will be temporarily connecting, or I'll be putting a logic 1 to these two switches. Okay, so for that I have PL3 and PL4. Okay, so PL3 and PL4 are those two pins. Okay, so that ports are being connected there directly. So based on that, we can derive some table. Okay, so for this, let me come to the section. So we have the two-wheel robot. So we have the two-wheel boat with us, and there are two wheels. Okay, so I am taking this as my left and this as my right. Okay, so with respect to one motor, if I consider one motor, there are two wires for that. For every DC motor, there will be two wires, and one will be a red color wire and other one will be a black color. Okay, so here the table is being generated by assuming that we have the four connections across PA0 and PA1, that is a left motor. Okay, and PA2 and PA3, that is my right motor. Okay, so if I need to rotate both these motors in the clockwise direction, I'm assuming that the red wire of both the motors should be supplied with logic 1, or the VCC to the motor should be applied to the red wire. Okay, so I need to connect this to the, and it is assumed that I have connected this red wire connection initially to PA1. So it is left red and this is left black. Okay, similarly I am assuming, or in this particular board it is connected like this, the right motor's right wire, red wire, and right motor's black wire is connected to the A3 pin. So for continuous motion, red should be made 1, so I am writing 1 1, and the remaining 2 will be 0. So I will be getting the value as 0x06. Okay, so if I'm passing this value to port A of the ATMEGA pin, then I can move this forward both in the clockwise direction, and the robot or this two-wheel boat will be moving in the forward direction. Okay, now if I need to bring back in the opposite direction, that is a backward direction, I need to reverse this. So the value can be 1001 because that is the red wires. Okay, so the value can be 0x09. Okay, So that is based on this assumption. I have derived this logical table, and we will be using these values throughout in this particular programming. Okay, so if I need to move the robot in the forward direction, I need to pass a value 06 to the port A, and if I need to move the robot in the backward direction, I need to pass it in the value 09. Left movement, I need to rotate. Okay, so here when we go for the leftward movement, as we discussed, okay, so this boat should be moving in the left direction. So right motor should move forward and left motor should move backward. Okay, so that is the right motor in the clockwise direction, that is 01, and left motor is moving in the backward direction, so that is value 01. Okay, so I will be getting 0x05. Okay, so likewise I have derived the entire table for left, right, soft left, soft right, stop. Okay, even there are two more, that is backward left and backward right, but I just derived for this. Okay, now based on that, I'm going to just write a small example where I can just move the robot in the forward direction continuously. So as we discussed yesterday or the previous classes, we will be defining the CPU frequency, that is FCPU equal to 14.7456 megahertz, and I have added the header file of the AVR microcontrollers. Then I'm initializing the port. So here I need to make use of the lower 4 bits of port A as the output, because they are connected to the L293D 1A, 2A, 3, and 4A. Okay, and indirectly it will be connecting the switching the power to the motor. Okay, so I'm writing the lower 4 bits is 1, so I'm not disturbing the upper 4 bits of the port A. So I'm performing a bitwise OR operation with the current value of the DDR A register with the required value 0x0F. Okay, then I'm initializing the value at this particular port to 0 initially. So these are two different methods. This is a method which specifically defines, and this is a short form. Okay, shortened bitwise operator has been applied here. Okay, then similarly I need to pass a logic 1 to the enabled pins, and we have seen that for the robot which I have, the enabled pins are connected to port L of the AVR microcontroller, and it is connected to port L's third and fourth bit. Okay, PL3 and PL4. Okay, so if you look at the value, we have the port register, port L register, there are 8 bits. Okay, 0, 1, 2, 3, 4, 5, 6, and 7. I need to make only these two pins as 1. Okay, so the remaining can be kept in the default status. So if I loop, this is 8, sorry, not this is 8, this is 1, and if I loop, this is 8. So if I write DDR equal to 0x18, that means I'm making the third and fourth bit of port L as output bits. Okay, so since I need not disturb the remaining bits, I am using the bitwise OR operator here. Similarly, I am making that values as temporarily written with logic 1 for this particular example. Okay, so I need to write 1 to that particular pin, so I'm writing port TL equal to port TL or bitwise or 0x18. Okay, then I'm writing the forward function. So as we told, to move the robot in the forward direction, I need to pass the value 0x06. Okay, so I'm writing that value, but before that I'm initializing that port, or the lower 4 bits of the port is made 0 initially. So why I'm writing this is because, let us assume that the robot is currently moving in a leftward direction, and we need to change the direction from left to right or left to forward. Okay, so in that case, we need to stop the robot for a small instant. Only then we can get that robot's motion in our control. Okay, if you are just suddenly switching the robot to move to a new direction from the current direction, we may not be able to implement that smooth transition in the direction change. Okay, that is why I'm initially passing a 0 value, which turns off the robot movement for a small instant, and at very soon I'm writing the value forward. Okay, and in this main program, I just written the program such that I'm initializing the port pins connected to the motor, and afterward I'm just moving the robot in the forward direction for an infinite loop. So if I burn this program, I'm writing this program, and if I'm burning this program to the board which I have, then what I can see is that the robot will be keeping on moving in the forward direction. Okay. Is it clear? If you're having any doubts, you may ask. Any doubts? Or shall I move forward with the real example? Would request some of the participants to respond. Can I move forward? Okay. So one of the participants told, okay. So we are going to have a demonstration for the movement of the robot which I have in this particular direction, that is an S shape. Okay. So let us first of all discuss the logic that is required for passing this or moving this robot in this desired direction. Okay. So I'm drawing it in a different manner. So the same thing. Okay. So I'm going to place this robot here. Okay, there's a two-wheel robot. So what it should do, when it starts, it should move in the forward direction, and after moving a particular distance, it should stop. Okay, then it should turn to the left side. So I need to perform a small left movement. Then again, it should stop. Just turn left, and it can again stop here. Then it should move forward, and after moving a particular distance, it should again stop. Then we are having the robot in this direction. Okay, let me draw it a little bit more. So we are stopping here. So we have the robot like this. Okay, now it should move to the left side. So again a left movement, then again stop, then it should go forward. So, and at this point it should again stop. Okay, so here you will be having the robot in this direction. Okay, now from this direction it should move rightward. Okay, so after stopping it should move rightward, and it will be aligned like this. On moving right side it will be aligned. So after moving a particular right movement for a small instant, it should again stop, then it should move forward, then again stop. Okay, so the robot is in this direction, so it should move rightward, stop, then it should go forward, and finally it should stop. Okay, so the sequence of movements starts from forward, stop, then left movement, again stop, then forward it should go, stop, left, stop, forward, it's up to here, then again stopping, then movement right, again stop, then forward, stop, right, stop, and forward, finally stop. Okay, so these are the sequence of operations that has to be performed. Okay, so for that I'm going to use the software. So this is a AVR Studio which I am using for burning this or programming to program this particular board. Okay, so I hope that you are visible with the screen. So that I am starting the program. Define FCPU 14745 600, then AVR IOH. There is no interrupt. So this is actually a modification of the program which I had done earlier. So that is why I have written this AVR interrupt, and delay is required. This AVR interrupt. Okay. Then pin configuration. Since I have the motors connected to the lower 4 bits, I am initializing the port A, lower 4 bits as output, and initially passing the value 0. Okay, that is the motors are not energized. Then to enable these H bits, I am using the port L, 3rd and 4th. So I'm passing the value 0x18. Okay. Now I have written the function for forward movement, that is stopping, and 0.6. Then left movement 0.5, right movement 0.a, stop. There is no need. So these are the basic 4 movements: forward, left, right, and stop is the basic movements which I require. Okay. Now to traverse through that S shape which is required, I need to first of all move in the forward direction for a delay of 4500 milliseconds. Okay, so this has been done based on some experiments. So that is why I have fixed this with delay. Okay, that was a trial and error. I'm not using the timer operation here, but actually when we go for the delay implementation, it depends upon the size of the tire that is available on your two-wheel boat. Okay, since we doesn't have more time for that, we are not going into detail of that. Okay, so I am calling a small delay which will transfers my robot for a distance of 76 centimeter approximately. Okay, then I am stopping it for after a small delay. I am turning left. Then again, after a small delay, I'm stopping it so that it will be rotating for an angle which is approximately 90 degree. Okay, it's not exact 90 degree, but approximate 90 degree. Then again, after left, soft stop, forward. Then again stopping. Then again left, stop, forward, stop. Then right, stop, forward, stop. Then again stop, forward, stop. So all the sequence has been implemented by using that providing approximately. Okay, so here this program will transverse the two-wheel boat which I have in the S direction. So actually this transfers has been done after a lot of trial and error method, because the robot's wheel etc which I have depends upon the floor. Okay, the movement of the robot entirely depends upon the floor surface. Okay, so if we have a smooth surface, the robot will be mostly transversing that exact S shape. If you are having some rough floor, like we have a 1 square meter tile which has been paved on the floor, due to the discontinuous point between two tiles, whenever the robot falls in between that, then the universal tire which the robot has may get slightly deviated from the exact movement point. Okay, so there may be a small change the shape, but all the sequence of forward, left, right, everything takes place smoothly. Okay, so after writing this, I can build this program. I can just save this first of all, file, I am saving, then I can go to build, then I can click on build solution. So here you can see in the output console window, the project has been building, and we will be getting the confirmation that it has been successfully built. Okay, so build, one succeeded. There are no errors or warnings in this. Now I need to burn this to my robot. So for that, I need to connect the robot to my system. Box. Okay. So here you can see the, so we have the screen here. Okay, so in this screen you can see the movement of the robot. Okay, so let me stop sharing so that you can see this in a higher manner. Okay, so we have the robot here, and from a system, so just 1 minute. So I'll be explaining how to do the programs in the upcoming sessions. I can show that. I'm just burning it. Okay, now the program is been burned so that the wheel has been stopped. Okay, so it has been successfully completed. The programming has been successfully completed. And now let me disconnect the programmer. And we can see it, how it is moving by placing the robot on the floor. Okay. So here you can see the robot has been placed on the floor. So it moves forward, then turns left, stops, then it again moves forward for a moment, then stops, left, movement, it's moving forward. As I told, since we have the floor in a rough surface, it's getting deviated. After right movement, it's stopping. So it has been successfully transversing to the S shape, for which we have programmed. Okay. So I hope that you are now clear with the working of that particular robot in the S shape in which it was transverse. Is it clear? So that was not the screen actually which I shared. I was showing a video. Okay. Okay, now the screen has been shared. Okay. So now we have done this example, or I have demonstrated this example of how how we will be transversing the robot in the S shape. So here our focus was how to program the controller so that with that program we are able to move the robot in the desired direction which we require. Okay, so here we had only 4 movements, but if we can go for any zigzag movement or any desired movement, we can have. Okay, so now with this basic thing, if by modifying some speed, by controlling the speed, that is here the robot was configured to move in all the directions with constant speed. Okay, now we can have a decision that in the forward it is moving at maximum speed, in the left side it is when it is moving leftward, it is moving in a slower speed. Oh, okay, or else in this when transversing through AB direction, it is having a one level of speed. For BC, it can have another level of speed, etc. Okay, so that is how we will be applying velocity. Okay, we won't be doing that experiment, so we can modify the same concept by controlling the velocity. And now if you are adding some ADC or some sensors, you can modify this logic such that your robot is able to distinguish or identify some obstacles in front of it, and it can take some decision like the left turn algorithm or right turn algorithm, which is a basic concepts that can be applied to configure the robot to solve a maze. Okay, so these are some of the projects which has been done in the mini project level, or as these are some of the ideas which can be used for solving some robotic hackathon or competitions. Okay, so now moving on to the velocity control. So basically how you can control the velocity of a DC motor is that if we have a motor that is been rated for operating at 12 volt. Okay, so most of the DC motors will be specified like this: 12 volt, 100 RPM, or some non-zero RPMs. Okay, so in this case, you can control the RPM or the speed of the robot of that particular motor by changing this voltage. Okay, so if I reduce this 12 volt to 6 volt, then at the specified conditions, you will be getting the speed reduced to 50 RPM because you are reducing by 50%. Okay, so if I'm reducing this further by 3 volt again, then the RPM can be reduced to 25 RPM. That is a 25% of 100. The maximum is 100. So when I'm reducing this to 75%, the 75% of voltage has been reduced, then the RPM has been reduced by total of 75%. So they are only getting 25 RPM. So this reduction in the voltage is a basic principle, okay, that you can use for providing or controlling the velocity of any DC motor. Okay, so how you can implement this variable voltages to the input of your DC motor that has been interfaced with your AVR microcontroller. Okay, so for that we make use of the concept of PWM, pulse width modulation. Okay, so here you can see if we have a series of pulse signal and if the width of the pulse is being changed, the average output that is obtained at that particular point varies. Okay, so the basic concept for that is if we have a continuous strain of pulse. Okay, so if I take this as the total time period and small t as the width of the pulse in that particular pulse strain, and let the maximum voltage be denoted by Vmax. Okay, then the average output V average is defined by V average is equal to small t by capital T multiplied by Vmax, or else this term is equivalent to the duty cycle of our pulse signal. Okay, so you can also write this as duty cycle multiplied by Vmax. So if I have 5 volt and I require an average voltage of 2.5, maximum voltage is 5 and I need only 2.5, then I can take 50%. Okay, so if I'm having a duty cycle of 50%, then what happens? If I'm applying that, then I can reduce the effective voltage into 2.5. Okay, so what I'm going to do is that I'm using this basic concept of this pulse to my L293D. Okay, so what happens is that I have the L293D. Okay, so for better understanding, I'm going to draw like this: 1A, 1Y, 2A, 2Y, and this is my VCC. Okay, so let us take it as 12 volt. That is the motor's voltage. So whatever be this value, if I'm applying a logic 1 here and logic 0 here, what happens is that here I'll be getting plus 12 and here we'll be getting 0 volt. That is a ground voltage. Okay, across. So if I measure the voltage across these two pins, that is a pin across the DC motor. Okay, so these are the terminals across my DC motor. Okay, so the effective voltage is 12 volt. Now this 12 volt will be available only if I am writing a logic 1 to the enable pin. Okay, so if I maintain a constant high voltage, what happens? For the entire duration I'll be getting a voltage of 12. Okay, but instead of maintaining a constant high voltage, if I am passing a square pulse like this of 50%, it is for 1 second. Let us take it as a 2-second time period. Okay, so 1 second it is on and 1 second is off. So what happens? If you observe the output that is obtained across this terminal, you can see here also for 1 second I will be getting 12 voltage. Then for another 1 second I'm not getting any voltage. Then again for 1 second I'm getting 12 volt, etc. Okay, so this is maximum 12. Okay, so with respect to the switching waveform, enabling by applying this pulse signal to the enable pin, here across the motor also I'm going to get a pulse waveform, and the average voltage can be determined by using this formula. Okay, so if I'm changing it from 50% to 75% on, then I'll be having a signal like this. Okay, so likewise, by changing the width of the signal that is applied to the enable pin of this driver, I can control the average voltage that is appearing across the DC motor. So this is how we are going to control the velocity of the DC motor that we are using in the boards. Okay, so for that we are going back to our timer module. During the discussions, we have already mentioned that we have two registers, OCRN and OCN. Okay, so OCRN is the output capture register, which is commonly used when we go for the PWM. Okay, so when the value of OCR is matching the value with TCNT. Okay, so when you are turning on the timer, so when we will be loading a particular value to the OCR, and the timer will be will start to increment from 0 voltage, and when the value of TCNT matches with the value of OCR, then the output of the comparator will be switching to either 1 or 0. Okay, and that 1 or 0 is available at this pin OCN. Okay, so whether before the matching between TCNT and OCR, the output value of the comparator should be high or it should be low. Okay, all those settings can be done by the programmer itself by using the register TCCRN, which we have discussed yesterday. That is timer counter control register. Okay, so in case of ATMEGA or AVR, there are 3 different types of PWM signal generation methods. Okay, the first method is known as fast PWM. Okay, fast PWM means there is a linear or a sweeping increment in the value of the TCNT, but once the TCNT or the counter register reaches the maximum value, then it is suddenly reduced to 0. Okay, that is a type of TCNT. So here you can see I have configured such that when the value which I have loaded to OCR N, that is output capture register, is, and when I'm comparing the value in the TCNT, that is a timer counter register. So if the TCNT value is less than OCR N register value, the output of the comparator should be 0, and when the value of the TCNT crosses the OCR, it should go to high. Okay, so that is a setting which I have done. So here you can see I am getting initially 0 voltage, and when the timer counter value goes beyond the value stored in the OCR, it is going to the high value. Okay, and it goes to the maximum value possible through the TCNT N register, and once reaching the maximum value, in the next clock pulse it is going down. So again the output will be going to the logic low level. Okay, so by changing the value that you're storing in the output capture register, you can generate pulse signals at the OCN bit. Okay, at the OCN bit with different width for the pulses for the PWM signal. Okay, so here it is shown that the maximum value for TCNT is FF, that is an 8-bit value. Okay, so if I am using timer 0 or timer 2, which are the two 8-bit registers, the maximum value that is possible in TCNT is 8-bit, and if I'm going for the timer 1, that is a 16-bit, then I can have the maximum count value in the TCNT as 65,535. Okay, but due to the various modes supported, there is a mode that is where even by using the 16-bit timer, you can limit the maximum value that can be possible in the timer counter register as 8-bit. Okay, we will be coming to that. So here you can see when the condition TCNT is greater than OCR, the output is positive and initially it is 0. Okay, so this is known as the inverting type of fast PWM. Okay, then the other two modes of PWM generation are phase correct and or phase and frequency correct PWM. So the basic difference between these two modes is how we are loading the value to the OCR register. Okay, but the working functionality of these two modes are exactly same. So here you can see whenever if I'm having a value stored in the OCR N register, whenever the TCNT value is lesser than this particular value, your output will be in one of the stage, one of the level that is been fixed by us, and once it crosses, okay, that is at this point you can see TCNT is higher, then it will be switching to the lower level or the opposite level, and it will be only switching back during the down counting stage and when it is going down. Okay, so here what happens is that there is an up counting phase and a down counting phase. Okay, in the fast PWM you are not having this slow down counting stage, you are having a steady down counting stage. Okay, that's the basic difference. So what is application of these two different types of PWM is that the first one, the earlier fast PWM method, this can be used for applications like your fading the LEDs. Okay, fading LEDs for regulation purposes, etc. Okay, you need to implement some voltage regulation circuit, etc., and you need to implement some control for that circuit. You can go for the fast PWM method, and this phase correct and phase or frequency correct PWM can be used for motor control. Okay, so basically in robot for real-time or precise applications, we should go for the phase control, phase correct or phase and frequency correct PWM method. But here we won't be going for that. Here we will be implementing the demonstrating the speed control of the robot using the fast PWM also. Okay, you can do it, but commonly you will be using that particular mode for applications like fading LED and regulation applications. Okay. So here we have these registers. So as I told, the PWM can be configured in AVR microcontrollers using the register TCCRN. Okay, so we have two registers for our timer module, TCCRNA and TCCRNB. Okay, so we have this first set of bits, that is upper 4 bits of TCCR1A register, which is going to control what should be the initial value in the OCN bit before, that is what should be the initial value of the comparator before TCNT is less than your OCR. Okay, so once you start the timer, at that time your timer is just incrementing, but it has not matched the value that is stored in the OCR. So at that time, whether you should have initial 0 or initial 1, that can be configured by using the value of these two bits. Okay, so COM1A1 and COM1A0 corresponds to the selection of the initial value that should obtain at the comparator for channel 1, and COM1B1 and COM1B0 corresponds to the second channel. And we are already told for each of the timer modules we have two PWM outputs. Okay, and this WGM11, WGM10, WGM13 and 12, these 4 bits of the TCCR register determines the type of PWM that is generated, whether it should be fast PWM or whether it should be phase correct, whether it should be phase and frequency correct. Okay, so let's look into this. So here I'm in the example, I'm using this particular configuration, that is 1-0 combination. Okay, A1 and B1 is kept as 1 and A0, B0 is kept as 0. So what happens is that initially when your OCR value and the value in the TCNT is not matched, okay, at that condition you will be having the value 1. Okay, the output of the comparator will be 1, and when it gets matched, then value will be going to 0. Okay, that means you have the comparator here, you have the OCR register, and this is your TCNT. Okay, so when TCNT is less than OCR value, you will be having 1, and when TCNT meets OCR value, it will be going to 0. Okay, so if you draw the graph, you have the OCR value here, and you can see the timer starts to count like this. For I am explaining about the fast PWM. Okay, so it starts from 0, goes to the top value. Okay, top I will be coming back. Then once it reaches, it goes down, and again it goes down like this. So this is the shape for the timer TCNT. Okay, like this. So if I'm assuming that this value is somewhere, it is somewhere like this. So up to this point, if you observe the OCN, OC1A, okay, here initially you will be having 1. When this meets, it goes low. Until this point, it will be low. Again, it will rise. So this is your OCR value. Okay, so at these intersects, it will be going down. Okay, so you will be having like this. So this is for the combination A1, B1 equal to 1 and A0, B0 equal to 0. So if I change it to 1, 1, the value will be low, high, low, high. Okay, so here you can see initially it is in the positive value, and then it is going to a logic low value. So we call this particular mode as non-inverting mode. Okay, and the other one is in the opposite of this, so it is in the inverting mode. So we are dealing with these two. So this table actually, if you go to the data sheet of the AVR microcontroller, you can see there are several tables like this for different types of PWM. Okay, so the first row and the last 2 rows are same for all the modes of PWM. There is only a slight variation in this particular mode. Okay, since it's not a topic in our discussion, we are not going into detail of that. Okay. Now, these bits WGM 10, 11, 12, and 13 determines a type of PWM, as I told. So here you can see when I'm loading the values as 0, the normal operation is will take place. And if I go to this combination 0001, then I can use a PWM. Okay, I can generate a PWM which is in the phase correct mode, and the maximum value up to which the TCNT can go is 8-bit. That is, even though you're using a timer 1 or a 16-bit timer, the maximum value up to which the counter register can count is an 8-bit representation. That is up to FF. Okay, if I'm using this combination, the mode and PWM facility is available, but the maximum value, the top value of the PWM can be increased from 8-bit to 9-bit. Okay, so likewise you can change here, and here you can see this is another capture timer control mode. Then we have the fast PWM here. Rather than phase correct, we have the fast PWM, and I'm using the fast PWM 8-bit mode. So the maximum value is FF. So with respect to this, the value that I can store to the output capture register is also limited to an 8-bit. Okay, that is, here I need to compare the value. So if I store this value as let us take an example 0x02FF. This is also an 8-bit 16-bit register for timer 1. Okay, so even if I store this value, the maximum value is only 0x0FF, and there is no condition where the values of these two registers will be matched. Okay, so that should be taken care. Okay, now if you need to make it into a 16-bit, you can see there are options here. So here is one of the mode. That is, if I'm configuring the W waveform generation mode bits in this particular sequence, I can have a PWM, and it can be operated in the phase and frequency correct format, and the maximum value for which the timer counter is going to count will be depending upon the OCR. Okay, that means it can go to the maximum possibility 16-bit also, but you can give any value. A 16-bit value can be given to the output capture register. Okay, but in this case, the maximum value is limited to an 8, 9, or 10 bits. Okay, likewise for fast PWM also we have such combinations, which is, since there are four bits, there are 16 combinations. I have only given a table which covers 13 modes here. Okay, so there's a continuation. So our discussion will be on this particular format. 0101, that is WGM 12 and WGM 10 are 1, all other bits are 0. Okay, so with this we may just look back here. So we need to make COM A1 1, COM B1 1. Okay, so 1010. Okay, 1010 means A. Then here you need to make WGM as 1. Okay, GM 10 as 1. Okay, this is a mode. So 10 and 12 are 1. So here I need to make this as this bit as 1. Okay, so if you look to the value that has to be written to the TCR register, the value is 1010 and 2 bits no values, then 01. Okay, so this can be, this is 1 and this is A. So TCCR 1A should be loaded with the value 0xA1. Okay, similarly, if you go to the next bit, this is your prescaler. As we discussed in the previous class, that is yesterday's class, how to apply the prescaler for the timer. The same thing has to be applied here also. Okay, so you can decide what should be the value, and in this combination you should make WGM equal to GM12 as 1 and 13 can be kept as 0. Okay, so these lower 4 bits are 0 and upper 4 bits can be configured as per your wish. Okay, so let's take a small example here, the same example which we discussed previously. I am configuring the output ports for the motor connection, then for the PWM. Okay, so L3 and L4 are the pins corresponding to, okay, L3 corresponds to OCR 5A and L4 corresponds to OCR 5B on my. That means I have timer 5 in ATMEGA 2560. Okay, I'm using that in my board. Okay, so in that case, they have by default connected the enable pin of the L293 AIC to L3 and for set 1 2, and the enable pin for 3 4 is connected to pin L4. Okay, and they are correspondingly the OCR 5A and 5B of the microcontroller. So that is why I'm forced to use timer 5. Okay, so forward direction is there. Then in the velocity, I am applying two different values. Okay, so I will be applying an 8-bit value, which will be controlling the left motor's speed, and another 8-bit value which will be controlling the right motor speed. And those 8-bit value will be assigned to the OCR 1AL and OCR 1BL. Okay, even though OCR is an 16-bit register, they are always accessed as a they can be accessed as two 8-bit registers, OCR 1AL, OCR 1AH. Okay, similarly OCR 1BL and OCR 1BH. Since we go for a fast PWM in 8-bit mode, we need to use only the lower 8-bit register of the OCR registers. Hence, we are only using AL and BL. Okay, so here you can see there is a significance unsigned character. Unsigned character means the maximum value can be from, or the range of values that can be stored in this variable left motor is from 0 to 255. Okay, that is unsigned character left motor and right motor. Okay, so this is a variable. So since I have declared the type as unsigned, this variable can store the value from 0 to 255. So this is enough for our purpose because we are using the fast PWM in 8-bit mode. Okay, so a character type of data type is enough for this variable. Okay, even if in your example, if you're writing unsigned integer left motor, the program works. There is no issues. Okay, but what happens in this case? In this case, you need only 8 bits since integer type makes use of 16-bit memory, or it takes 16-bit. Only 8-bit is required. Another 8-bit memory location is a waste. Okay, so that it is going to affect more memory usage when you compile the program. Okay, so understand the requirement of the memory and assign the exact data types in our program. Okay, so we will be assigning the velocity like this, and in the timer program, timer configurations, because we need the timer module to be configured. So I'm initializing the timer counter of the timer 1 with 0 0. Then OCR 1AL and OCR 1B is initially given 0 0. Then TCR 1A with A1 and TCR 1B with 0x0B. So 0x0B means 0x0B. That means upper 4 bits are 0, lower 4 bits we will be having the value 1101. So this is to WGM 112, and these 3 bits for your clock selection. Okay, that is a prescaler. So you configure the timer module, and now when you come to the main program, here you can see I am initializing the port first of all. Then, sorry, there's a small mistake here. I need to call the function for timer configuration also. Okay, so after this port initialization, I'll be calling the timer configuration. Then in the while loop, I am calling forward. Okay, so forward is there, but you can see OCR 1AL is equal to 0. OCR 1AL equal to 0 means you are not setting any value. Comparison value is always 0. Okay, so initially your timer won't be working, but when you pass this velocity 255, then that value is stored to the, so this function on execution goes to here, and the 255 is applied to OCR 1AL and OCR 1B. So based on these two values, your timer will be operating and it will be performing that generation of the PWM. Okay. So let us have a look into the live example here. So I have a project for demonstration. So that's a second experiment for demonstration for today. So here this is again a project where the speed, the varying duty cycle, like not duty cycle, the change in the speed is been denoted in the LCD also. Okay. So I am initializing the FCPU. So this is basically the work that our team of robotics has done for the Yendra task-based challenge, okay, training sessions. So we have the LCD module here. So I'm just explaining the necessary parts. So we have the motion pin configuration for the motor interface and the PWM. Then we have a switch. So here this example is such that I have a switch on this board. When I'm pressing the switch, initially it will be at 0. That is, initially the motor won't be working. Then for first switch, the speed will be increased a little bit. Then for second switch, it will be again increased. Then it will be going to the maximum speed. So there is a step-by-step increase in the speed of the motor rotation. Okay. So for that, I am initializing the switch that is available. So I am making that particular switch as an input port, input pin, and I'm activating the pull-up resistor value. Okay. Then there is a port initialization which takes care of initializing the port pins connected to the motor as well as the switches together. Then the timer has been initialized with all the values as we discussed right now, and we're starting the timer. And there is a velocity function which assigns the value to the OCR register, and this is a forward function corresponding to for moving the robot in the forward direction. Then this is for the stop. Then we have the motion control. Okay, so it checks whether the switch is pressed. Okay, so the maximum press possible here is 9 times. So based on each of the press, so initially it will be 0. For first press, the value will be incremented to 63, and a new value is assigned to velocity 3f. Then if I'm pressing again for second press, this velocity value, the value that should be written to the OCR register, is updated again. For third press, it is again updated, and fourth press, it is going to the maximum possible value. It is 255. Okay, then I can go for 255, but it is 254 based on the requirement here. Okay, then on the fifth press, it is reducing down. So if you look in the detail, initially the motor won't be working, then it will be just increasing, then one more increase, and final increase, then it is coming down, down, down. Okay, so they can see that the motor is reaching the maximum speed, then it is slowly reducing to the lower speed based on the switch press. Okay, so that is the basic function, and each of the status should be indicated in the LCD. And the main function, the programs are to configure the LCD pins, initialize the LCD. Since it's not a topic that we have planned for the session, I'm not going into details of that. Then I'm initializing the ports, initializing the timer, then I'm just calling the motion control. That is a main sequence. Now let me build this program. Okay, so I have built this program. So this project is there in the desktop FDP folder, demo velocity experiment 2. Okay, so hex file has been created. So in the command prompt, I'm using AVR dude. So I'm typing stk run, okay, space. Then I should go to the folder. There is an FDP folder, demo velocity experiment 2, debug. Inside this, I can see the hex file. Okay, so what I'll be doing is that I type the command stk run, and I'm just dragging this. Okay, this is an easiest method, dragging that file here. So that location is there. Now I need to turn on the board, and I'll be typing enter in my command window prompt. Just a minute. Sorry, system was not connected. Connect this. So again, I'm running that same program. So you can see the program is being burned to the memory of the controller. So all the fuses are burned, and thank you. So this shows that the uh, program has been successfully burnt. Now I can show you the demo. I'll be turning on the video. So here we have the board with me. Okay. Hope that you can see the video. Can someone say that? Give a response that you can see the video. Is it visible? Yes. Okay. So now I'm going to press the switch. So please, I have not shared the video. Rather, you can see it from the video is been turned on the ID CRR. Okay, let me then share my video screen. Okay, fine. I think now the screen is visible to you. Okay. Just 1 minute. There is some issues. I need to make this video to. Okay, fine. You can see here. You can just look to the motor. Okay, you can observe the wheel. So I'm pressing the switch here. So it's not working because the power is very low. The battery is very weak. Now I'm going to press one more. So you can see the motor is rotating right now. Okay. So this is a second level of speed. Now if I'm going to press the switch once again, you can see the motor rotation, the speed of the wheel movement has been increased again. Okay, so that was the maximum speed available, and since the battery power is little bit less, you may not be able to see the highest speed. Okay. Now if I'm pressing the switch again, you can see the speed has been reduced. Okay, now you can see it's very slowly moving. It's moving very slowly. I'm pressing once again. It has gone to the stop status. Here you can see it is a bit very slowly. It is moving. You can see that gear. Here you can see those gear movements. Very slowly it is moving. Okay, it has been stopped right now. Okay, now it is in the stop status. So that's how we can. That's a demonstration of how you can control the speed of the DC motors. If you're having any doubts, you may ask. So in between, I think there was a doubt query. If you have 4-legged robot, single actuator peg leg, and want to turn left or right, then how do you do the same? Sir, basically, this concept of motion is different for the wheeled robots and legged robots. You're talking about the legged robots. So in that case, the entire dynamics, kinematics and dynamics of robots are different. Okay, so I hope that in yesterday's class, yesterday we had the session from Inga Robotics on kinematics and dynamics of industrial robots. So those concepts should be applied when we go for the legged robots, and in that case you should consider the gravitational force and other centrifugal forces and other things. Okay, so all those nonlinear effects should be considered for controlling the movement of legged robots. In this wheeled robot, we need not go for that. In wheeled robots, the major topics or major factors that has to be considered are the torque of the motor, then the weight of the robot, size and weight of the entire robotic structure, and the surface in which it is going to move. Okay, so if we need to move the robot on a irregular surface or a rough surface, we need to go for wheeled robot with width, with a higher width of for the tires. The wheel should be having more thickness, and if it is a smooth surface, then you can go for the thin wheels with the wheel robots. Any more doubts, or else we may go on to the ADC section quickly. Shall I move forward? Okay, so moving forward, next is to ADC. So in our AVR microcontroller, we have a 10-bit resolution ADC. That is, for any given analog value, we'll be getting the digital values represented in 10 bits. Okay, and the conversion time taken for this analog to digital conversion varies from 13 microseconds to 260 microseconds. Okay, and depending upon the AVR microcontroller that you are using, you can either have a 6-channel ADC or you can have 16 analog inputs. Okay, so for ATMEGA 328, we have 6 channels, that is A0, A1, A2, A3, A5, A4, and A5. And for ATMEGA 2560, we have around 16 channels. Okay, that is A0 to A50. Then we have the left or right adjustment, which I will be explaining in the coming slides. And the clock required for the ADC module to operate properly is in the range for 50 kilohertz to 200 kilohertz. So this is one of the area which you need to consider while developing programs, is that we need to prescale the clock signal that is applied to the ADC based on this particular range. Okay, so using your crystal oscillator, if I need to operate the ADC at 200 kilohertz from the available prescaling ratios by setting some bits, we'll be looking to that. So you should select the appropriate prescale ratio. Okay. So the steps in that is that, first of all, you need to enable your ADC by setting the bit ADEN, which is present in the register ADC SRA. Then after that, as I told, this is not ration, it is ratio. So you need to set the required prescaling division ratio for your clock signal that is applied to the ADC by setting the bits ADPS. There are 2 bits known as ADPS. Using the different combination for this ADPS bits, you can, that which is available in ADC SRA register, you can determine the prescale value. Then you can select the analog value, reference analog value, by setting the bits of RFS X bits of ADMEX register. Similarly, the left or right adjustment can be selected by using the bit ADLAR of ADMEX register. Then you need to select the ADC channel, okay, so the ADC input channel. Then you need to start the ADC conversion by setting the bit ADSC bit of ADCSRA register. And finally, you can wait for the bit ADIF in ADCSRA register to be 1 so that the conversion has been completed. So once the completion that has been completed, then you can go for ADCR, that is data conversion register, ADCR register, which contains the converted digital value. Okay, so this is the ADMEX register. So here you can see that in the MUX register we have MUX 0 to MUX 3. So this is a screenshot of the register of ATMEGA 328. So in ATMEGA 328 we have only 6 registers, 6 channel. So to select the 6 channels, you need only 3 bits: 000, 001, 010, 011, etc. Okay, so they have provided 4 channels, so you can use it for an advanced version also. Okay. Then this is the ADLR register which selects the left or right adjustment, and this reference S1 and S0 is going to select the analog reference voltage. Okay. Then we have the ADC SRA, the control and status register. The first MSB bit selects the enabling of the ADC module. Then ADIF indicates the completion. Then we have the lower three bits ADP S0 to S2, which selects the prescaling division ratio. Okay. So here you can see, based on this combination, the division factor can be selected from 0 2 to 128. Okay, so that is depending upon us. If I need to have the clock frequency of 50 kilohertz, then I need to select a appropriate division factor. Okay, then as I told, when I'm making ADLR equal to 1, these are difference in left and right adjustment. So by default, what happens is that we have the register. So this is your ADC data register. Okay. So we have 8-bit register because we have 10 bits. So by default, all the first LSB 8 bits will be in the lower register, and upper register will be containing 2 bits remaining blank. Okay. So in this, you can see the data is aligned to the right side. So if I need to make it to the left side, I can make ADLAR equal to 1. So what happens is that these 2 bits will be aligned here and everything will be pushed. So you will be having 8 bits in the upper register and these 2 bits alone in the LSB register. Okay, so here the data is aligned to the left side. Okay, so that is a difference between left and right adjustment. Okay, so now I'm going for the demonstration version. So I'm not going to explain the code fully. So I have an example for ADC. Since the time is exceeding, I'll be just showing the demonstration. Okay, so let me open the code and quickly building the code. So it has been completed. So just a minute. Comments we are doing. SDK run space, and I need to go to the experiment debug. Okay. So I need to just burn this code. So I am burning the code. So here on this, I have a sharp sensor, that is an analog sensor. So here, based on the distance of the object in front of the this sensor, it will be displaying obstacle is very far or it is near. Again, they'll see. Okay. So let me come to that. Here you can see on the screen, it is showing that obstacle is very far. Okay. Now I'm going to place my hand in front. So it is showing that obstacle is near. So a little bit. Okay, now the distance is in another region. So it is showing that obstacle is far. And if I'm moving so far, then showing that obstacle is very far. Okay. So this is an example of how the ADC can be interfaced with the in robotic applications. Okay. If you're having any further doubts, you may ask. So by this, I have completed the topics which we have planned for the demonstration or for this 5 days FTP on how to apply embedded systems for developing robotic applications. Okay. So on this occasion, I would like to thank all my teammates in this Center of Robotics Research and Consultancy. who has given me immense support for making the session into reality in a short time, that too in the online mode. And I also wish to thank the organizers of this FTP for providing me a chance to share the knowledge that I have to the participants.
Good evening, sir.
Yes, good evening, sir.
Good evening, participants. Participants can unmute your mic and ask any queries regarding the session or comment doubts in the chat box. Meanwhile, the feedback link is provided in the comment box. You can use it and mark your attendance. Okay, then I think we can wind up the session. So respected Professor Ramesh CR, Head of Vidya Center for Robotic Research and Consultancy, and dear participants, we are having for the first 3 days a nice session by Professor Ramesh with his vibrant hands-on sessions on embedded system for robotic application. We were going through very informative and fruitful sessions. I'm sure that Ramesh sir enriched all of us with various aspects of robotic design and its programming in a simple and lucid manner. Thanks a lot, sir, for your wholehearted effort to enlightening us with your knowledge. Thank you, sir. Thanks a lot. I thank all the members of Vidya family and AICTE for providing such a wonderful opportunity for learning. So today's session, we are winding up. And remember, there are 2 sessions tomorrow forenoon, and the validity function along with the test is scheduled as tomorrow afternoon session. So thank you all. Thank you.
कुछ कुछ अच्छा ओके